A very good day to all. We are a group from CME University, Malaysia, and we will be briefing you through our project on the production of sustainable aviation fuel from palm oil trunks via gasification fischer trap synthesis. And this slide highlights the application of using FT synthesis, where one of our end product will be SAF, which serves as a direct replacement for conventional jet fuels.
Okay, from the right diagram, we can see that the SAF demand grows rapidly to achieve net zero by the 2050. From the left table, we can see that the Asia have the largest supply gap. Consider the distance and other factors. The Asia is our ideal market. Our target is to produce 1.5 million tons SAF per year to be one of the largest SAF supplier in the Asia.
So for problem statement, the aviation industry actually serves as a contribution to carbon emission, also having low yield process, and in Malaysia there's actually limited SAF supplies, but actually there's a high potential market. So for our objective is that we will use renewable resources, we will develop detailed engineering designs for unit operation, and also we will try to work on our plant cost capacity.
For the process flow, here is the input and output of the overall production of SAF. It is divided into 6 main stages. The first one is pre-treatment, where we will grind the raw materials and do pyrolysis. And next is going through gasification, where we will burn under a high temperature. Next is reverse water gas shift, where we will obtain more carbon monoxide. And then we remove the acid gas. And next we go through the fischer traps, where we will obtain a shorter carbon chain. And then next we will purify our products, which includes the SAF. So here is some of the process conditions of each of the units. And for material of constructions, there are several considerations, which are corrosion resistancy, cost effectiveness, high temperature strength, and wear resistancy. Therefore, there are 4 main materials: stainless steel 316304 mainly for reactors, Inconel 600 for fuel heat exchangers, and silicon carbide for cyclone.
Okay, here is our PNID diagram. Such as for this distillation tower, we can control his pressure, temperature, flow, liquid level with the help of the valve, and also we add the pressure relief valve for the safety.
And so for this is hazard analysis table, I will give an example on the FT reactor when it's high flow. So this is caused by the failure of control valve, and will lead to overpressure in reactor. And what we do is we will install flow meters, and also we'll perform regular inspection and maintenance. And after all the hazard that we have done, we'll move on to the mitigations, where for inherent, an example would be we will install cyclone separator for removing dust, and also for passive, we will design equipment to cater for worst case scenario, and we will install multiple cooling system for the FT reactor in the active part. And for lastly, procedural part, we will generate SOPs and also implement strict safety guidelines. And for plant layout, there are actually several considerations as shown in this table, and after factoring all of it, we have chosen the Gebeng Industrial Park as our site location. And this is a more detailed plant layout where we follow the code of practice and also the industrial guidelines. And this will be the layout for our equipment spacing, where we have met all the specifications listed.
Okay, to deal with the gas waste, solid waste, and the liquid waste, we are focused on the environmental friendly design. Based on the law of the Malaysia, we try to reuse the product and reduce the energy cost in the process. And for the economic potential, we decide our price is lower than the market price. By this, we can get our payback time is about 5.8 years. ROI is about 19%.
So when it comes to the conclusion, our process is feasible with a capacity of 331,000 tonnes per year, and we've also done a carbon analysis using Aspen. And for economic, it's also feasible. As mentioned, payback period is 5.8 years, and all our plant design is complying with the regulations. And we've also done a heat integrations or heat analysis from the heat exchanger, where we'll obtain 31.5% energy savings. And our process is also scalable with elements of sustainability in our process, which are 3P: people, profit, and planet, which all leads to a circular economy implemented in our process plant. So that is all from our project. Thank you so much. My name is Gabriella Ivana Sugianto.
My name is Zhao Yingzhan.
And my name is Kexin.
We are students from CME University, Malaysia. Thank you.